I'm very excited to be here today to share my research with you. My talk today is on the dynamics of roasting, how roast profiles affect the physical and chemical properties of our coffee. So before I begin, I'd like to introduce myself. My name is Laudia, and I'm from Ghana, and where I did my bachelor's in food engineering. In 2019, I moved to UC Davis for my master's in biological systems engineering. And for my master's, my research was on green coffee storage and transportation. So I'm currently continuing with a Ph.D. Also in UC Davis with a coffee center, but this time I'm working in coffee usage. So for one of the restriction together. Now, before I begin, I'd like to talk briefly about the coffee center. So for those of you who don't know this, the University of California Davis has a coffee center that was established back in 2016. And this slide here, it's a snapshot that summarizes what we have going on at the coffee center. So we currently have this building here at the Southern Real campus, where we do scientific coffee research, which is what I'm talking about, the research I'm talking about today. And then our main goal as a coffee center is to create a world-class facility for coffee research without any one place. And so for the past 3 years, we've been trying to generate funds to renovate the building that we have to make it into the world-class facility that we want. And so far, we've gotten the coffee industry has been very supportive. And on the right side, we have all of our buildings who are getting stimulated really. And I'm happy to announce that this May, we are doing a grand opening ceremony, and all of you are cordially invited. So here's some finished architectural renderings of what the new building is going to look like. And as I said, our main goal is to have all the science research, everything under one canopy. So we have various labs that will be ranging from, we have the Total Innovation Lab, we have a green coffee lab, a Pete's Coffee Pie Roasting, and a lot of content. So please do come by every day. Okay. So again, before I get into my research, I'd like to emphasize that the project I'm about to talk about is project I'm going to talk about took a tremendous amount of effort and collaborations from a lot of people. So here's our hosting project team, and we have 3 different professors from different departments that are collaborating on this project. We also have a team of undergrads who really help with the data collection and analysis. And lastly, and most importantly, I like to say that without Probat's financial assistance, I wouldn't be able to do this research. So thank you to Probat. Okay. So my presentation today, for the first part, I'm going to talk about the motivation and the larger vein of my work. For part 2, I'll be discussing the experiments and my methodology. And then this is a big experiment. We have a lot of results so far. So for the purpose of this talk, I'm going to focus on 2 parameters. That's titratable acidity and PAC-E. So I'm going to discuss how different roast profiles affect the titratable acidity of your coffee. And then lastly, I'll talk about how roasting affects power. And I'll discuss a discovery we made during our experiment, which we are calling the universal market. So let's get on with the motivation. If you've taken a brewing class or you are into coffee brewing, you probably are seeing this chart. This is the coffee brewing control chart. Now, simply for what this chart does is that it controls the sensory properties in your cup of coffee. So the figure on the left is the old version of the brewing control chart by what pipe related to today. And this figure on the right is the new and improved version by this pipe itself from 2023. Now, I also want to familiarize you with this chart. On the vertical axis, it has the TDS or the strength of your coffee. And then on the horizontal axis, it has your extraction. So basically, how much of your solids went into the liquid phase of your coffee. On the diagonal axis, it has brew ratio. So simply put, why I use this chart is that if you know, or if you have a certain strength of your coffee for the vertical axis, and you have a certain extraction yield, and you know your brew ratio, you'll be able to predict what your coffee is going to taste like, the savory properties. Now, I'm sure most of us in this room, or the people who do roasting, is that even though you could use this chart to control your brewing, roasting is a more important process when it comes to manipulating the flavor in your coffee. So this brought me to my big research question that why didn't we have a roasting control chart? So that's my overarching research question. How about we summarize what the complexities being roasting, and then we create a chart that looks like this. That way, every start anywhere in the world can pick these charts to be able to control what their roasted coffee is going to come out looking like. So here's a hypothetical coffee roasted control chart that the digital might probably change at the end of my research, but this is what we envision it to look like. So what we are hypothesizing is that you take a certain parameter of your green coffee, let's say your moisture content or your sugar content on the x-axis, and then you take a certain roast metric on your y-axis. And by these things, you should be able to predict what your coffee is going to taste like once it's roasted. So this is the overarching goal of my research. Now, the steps we've taken to answer this question is what I'm going to share with you today. So let's go on to the experiments we've done so far. Before we can predict and correlate things, we first need to understand exactly what is happening in roasting in terms of the chemistry and in the physical analysis. So for the phase one of this project, our tertiary was how the different risk profiles affect the physical and chemical properties of your coffee. The way you roast your coffee, what exactly is it doing to the chemistry? So to answer this question, we took 3 different coffees. We roasted it 7 different ways, and then we measured 15 plus physical and chemical measurements. That's to be able to see what is systematically happening as a roast. Now, we took coffee from 3 different origins, and then in the roast profiles, we took 7 common industry roast profiles, and we did each roast for 16 minutes. We took 16 minutes because we wanted the roasting to go on long enough for you to go from green to black, basically burnt coffee, so that we have a full picture of what is happening. And then we sample every minute during our 16 minutes roast. So we'll do our roast, and then every minute we'll pick a sample from our experiment. We take these samples to the lab and measure different things like water activity, moisture, titratable acidity, color, etc. Now this experiment lasted for about 4 months. So we wanted to make sure our green coffee isn't changing during that time. So what we did was we stored our green coffee in environmental chambers at a temperature of 25 degrees Celsius and a relative humidity of 60%. And this represents typical greenhouse conditions. So we wanted, the only thing we are varying is our roasting process. So we tried to keep our green coffee the same. Now, onto our roast profiles. What I mean by roast profiles, traditionally, it's basically the time temperature variation during the roast. So what temperature you are roasting at, how long you are roasting at, that's what we are calling roast profiles in this experiment. This is a figure showing the 7 different roast profiles that we picked. Now, on the vertical axis, on the y-axis, we have the temperature of the roast, and then on the x-axis, we have the roasting time. So in this case, we have about 16 minutes. I'd like to explain the different sections that we have, those different standard or even the legend that you see down here. So before that, the check marks that you are seeing in each graph is the roasting temperature. It's how the temperature is changing as you roast. So when you put your coffee in the roaster, because the coffee is colder than the hot roaster, the temperature drops first, and then you wait till the coffee and it starts rising. So that's why you have that check mark going on. And the black curves that you see is called rate of rise. So what we are defining as rate of rise is the change in temperature per 30 seconds. So that's the black curves that you see. Now, for the different phases, the green bar that you see on top of each graph is we are calling it a pre-color change phase. So when it starts roasting, your coffee starts going from green to yellow. So that green phase is called a pre-color change phase. And in industry, it's typically called the drying phase. And then we have the yellow section, which is color change to first crack. So as the beans start to yellow away, and as it goes forward brown, you hear a crack or a popping sound, and that's what we are calling first crack. So the next phase is color change to first crack. Then the third phase, as the beans keep browning, you hear a second crack or a second popping sound, and that makes us from first crack to second crack. And then the darkest phase or the darkest section on each graph is basically what happens after second crack. So when we are copying black alone, typically. So now I'm going to go through the 7 roast profiles that we use, the why we picked those. So our first roast profile, which is the figure A, the topmost one on the left, that's a fast start. And we are calling it a fast start because to follow the descriptions, please follow the black curves. So you see that it has an initial heat application. So the rate of rise is high at the beginning, and then as the roasting goes on, the rate of rise drops. So we are calling that fast start. Our second roast profile is the slow start, which is the opposite of the fast start. So the rate of rise is lower at the beginning, and then it keeps increasing as the risk goes on. We also had a medium risk profile, which kind of falls between the fast and the slow. Our fourth risk profile that gets explored with the production risk. Now, this risk is what is typically used by the big industry companies. So what's the thing about this risk is that once they set the energy of their roasting, they don't change it. So they just let the risk run, and that's what we replicated with the production rules. Now, apart from these common industry risks, we were interested in looking at how roasting defects also affect your coffee. So there are some popular defects that we looked at, and the first one is exaggerated flake. So being a roast, sometimes if you pay attention to the black thread, you see that there's a sudden rise in the rate of rise here. So that when that happens, it's called a flake. And then the second defect we looked at was negative rate of rise, meaning sometimes in a roast, your roast condense go off. The roast will just stop, and you have to start again and continue. So the question we had was, when these, in quotes, bad things happen, would it really affect your coffee? Like how people in the industry believe, for example. And then the last profile that we considered was the extending layer, which is popularly known as the baked profile. So what happens here is that at a certain point in the roast, especially in the first part, you see that the rate of rise is kind of constant. So your coffee is just kind of baking as we are roasting. So we took all these seven profiles to see how they affect our coffee roasting. Now, this is a figure that shows our seven roast profiles superimposed in each other. So there you can clearly see the differences with the seven profiles that we considered, especially looking at the different faces that we have. And at this point, I want to give a shout out to our head minister, Timothy, who did a very good job in doing all of these roasts within our experiments. So now I'm going to talk about the experiment itself, what we did on a typical roasting day. So on a roasting day, we roasted 4 kilograms of coffee. And then for each minute of the 60 minutes, I'll take a sample out with the triad as you see in this picture. So the next step is that we split the sample that comes out into about 30 grams. So we split this 30 grams into 2 teams, 2A and 2B, and here's why. Because we are interested in measuring only what is happening in the roaster, we didn't want to have any chemical reactions happening once the coffee next the roaster. So to get this, we froze our sample in liquid nitrogen as soon as it got out of the roaster to stop any further chemical reactions from occurring. And then we kept it on dry ice while we collected the remaining samples. We took our sample to the lab, we measured the size distribution, we ground our samples and measured the color. We then ruled our sample, we measured TDS, titratable acidity and pH, and then we did extraction with methanol. I think some of the words are not very clear, so yeah. We then did chemical measurements using HPLC analysis. Now onto the tube that we did freeze. So we chose not to freeze the second tube because we wanted to use this sample for moisture measurements. Like freezing and thawing would affect our moisture value. So for this sample, we quickly brought it to the lab. We did bulk density. We did water activity. We measured negative spectroscopy. We ground our sample, and then we measured moisture content. So here's a video that is showing like a typical experiment day for us in the discussion center. So here I'm pouring 4 kilograms of vapor from our Probat P5, and then we have our heading structure with it. So every minute of this roast, I'll pick a sample just like this, and it'll weigh about 30 grams. I'll then take it to our team of undergrads, and then we split the sample into the 2 tubes, tube A and tube B. The tube A comes out to about 8 grams. Tube B will be about 5 grams. Now the tube A goes on to get frozen in liquid nitrogen because we want to stop any other reactions outside the roaster. So this is us dipping it in the liquid nitrogen to freeze the sample. And then we store the sample on dry ice while we do the entire process. So this process is ongoing. We do the studying 3 times for each waste that we did. Now we bring it to the lab. This is the freezing sample. So we do that, we measure the size distribution first. And then we grind that sample using water food grinder with the lab. So we do this so we'll be able to determine the color of our sample, which is the next step. So here we have our ground sample, and then we are using the Hunter spectrophotometer to determine the color, and then we coordinate to our color. After measuring the color, we do our sampling full immersion boom, and then we measure the TDS of our sample, and then we titrate our sample with an automatic titrator. And then it goes to the chemistry. So this is all still the frozen sample. So it goes to the chemistry side, and then we use 40% the panel for extraction. We put our sample through sonication to separate the liquid and the solid, so that we'll be able to do the HPLC analysis. So in the sonication process, we then put it in a centrifuge to really separate the liquid portion from the solid. And then we'll do the extraction, then HPLC analysis for all the clinical measurements like proteins, lipids, etc. So now let's go to the tube that we've been offering, the moisture line. So for that, we carefully determine the water activity using the 40 Apollo meter, essentially. The next, we determine the bulk density of the sample. So for bulk density, we measure the sample mass, and then we read the volume using the energy cylinder. Now, each of these states were done with triplets, 3 times, to be able to move with statistics. So this is definitely making the bulk density of our sample. Then from here, we look at the moisture content using the oven method when you grind our sample and put it in the oven for 16 hours. So you look at the mass before and after. So you can see in this shot the progression of the samples that we have. So we have it from sample 0, which is the green one, all the way to sample 16. So this is one root. So this is like the day showing for one root. So to summarize all that we did in this study, we first took coffee. That was the CP4 Uganda. So I forgot to mention the 3 origins of it. So one was CP4 from CP4 Uganda. We applied that 7 days profiles and we did this 3 times, so that gave us 20 minutes. Now, after this first set, we linked that our results and we saw that some of the risk profiles were the same. So we picked the 3 that were most different and applied them to the different origins of coffee. So for the next set of experiments, we took out coffee from El Salvador, that's the process. And then we used 3 profiles of Spanish instead of 7, and that gave us 9 minutes. We did the same thing using Sumatra wash coffee. So at the end of the day, this 39 list with our 17 samples gave us 663 samples for this first phase of the experiment. Now we did 20 different measurements for each sample, so we ended up doing about 13,260 measurements. And once again, I want to emphasize that. Might as well they get to get example what they do. So this is impossible without another one to live it and that's the lab is a composite. So on to the best part, the results or what we've seen so far. Now looking at what we've measured of all the tracing measurements, we still have a lot of data that we are currently processing. So for today's talk, I'll be focusing on 2 parameters. The first one is titratable acidity. I like to say that titratable acidity is more important than pH. And most people do not know this. Most people are more used to measuring pH, which is the negative variant of the concentration of hydrogen ions. So I want to emphasize that pH only measures strong acids. Compared to titratable acidity, it measures the total amount of acids that you have with your coffee. So here are shots of how to be the titratable acidity. After brewing our roasted coffee, we put it in this automatic titrator and it added base in drops. That's sodium hydroxide until it to neutralize all the acids in our coffee. So that's what titratable acidity means. It's how much base it takes to neutralize the acids in your coffee. Now, titratable acidity, or TA in short, measures both strong and weak acids. And this is why it's a better parameter than pH when it comes to coffee. Now, when someone like wondering, why do you really care about titratable acidity of coffee people? TA strongly correlates with perceived sourness in coffee. So there was a study that was done at UC Davis, and it shows that from like a consumer perspective, consumers are able to tell or they are able to point out more perceived sourness in a group of attributes. So there was this paper that shows how perceived sourness correlates with pH in the first figure, the first graph, and how perceived sourness correlates with TA. So if you look at this first study, you can see that there's a negative or low correlation between perceived sourness and pH, as opposed to this one that shows that there's a very high and strong correlation between perceived sourness and pH. So from today, please share more about titratable acidity. Okay, so here are the results of titrated acidity that we have. And I chose to show just 4 out of the 7, just so that you can see the graph properly. But whatever is happening in this 4 is also happening in the other 3 profiles that is innovation. Now, this is the results of titrated acidity being used based on the different risk profiles that we have. On the y-axis, we have the volume of base it took to recharge the acid. So we have the titrated acidity on the y-axis. And then on the x-axis, we have our wasting time or our sampling frequency. We have our 0 to 16, that's 17 samples. Now, the first results that we had was that there was a similar trend in titrated acidity for all the risk profiles we looked at. So you can see on the graph that titrated acidity starts increasing slowly, and then when it gets to power change, which is this phase, it kind of shoots up to a maximum, and then it drops again. Now, the scientific reason for this is that it's a breakdown of carbohydrates into acids like acetic and formic acids as you use. So that's what's happening. Another result that we saw was that the titrated acidity always peaked at first graph. So if you take one thing from my talk today, it should be that when you are roasting a here first graph, that is when you have one layer of coffee is most acidic. So these vertical lines or bars here, they show when first graph starts. So you can see that the sample right after the first graph is where you have the peak or the maximum titratable acidity. The third result that we had was that by the time you get to second graph, the titratable acidity has come down to almost the initial value that you started with. So again, practical application. As you roast, if you want to have very acidic coffee, you stop your roast during first graph. That will translate to like light coffee. Medium coffee or light to medium. And then if you want coffee that's in the not acidic, you will stop during second graph. So that's all our resources to the acid. That's how one can apply it practically. Now, if you pay attention to the peaks or the maximum values of these curves, you see that they were always between 4 and 5 of titratable acidity, where the peak titratable acidity was similar for all various profiles. So we zoomed in into the TA, and this is what the results show us. So this figure has the peak titratable acidity on the vertical axis, and then we have our different risk profiles and origins on the x-axis. And then these are the 3 copies that we have. And then these letters here show the statistical significance of our sample. So for example, if you see the same letters, like maybe an AB, it means there's not much difference. There's more statistical significance or difference between the 2 samples. And then if they have different letters, then it means that. Now looking at this figure, you can see that almost all of our samples have the same peak titratable acidity. So what this is telling us, the phone will start and that. What is telling us is that the maximum amount of acidity that you could make and could have used is the same, regardless of how you roast your coffee. So this means that the maximum titratable acidity is not dependent on your roasting method or your roasting process. Okay. Now to answer the big question that we had, which was, do roast profiles affect the behavior of titratable acidity? By superimposing all of our titratable acidity results on one graph, we can see that the different roast profiles are making our acidity behave in different ways with the roasting. For example, if we focus on this roast profile, which is a slow start, at minute 8, it has a titratable acidity of close to about 2.5. But if you were using, let's say, the negative rate of rise, I don't advise that you choose the negative rate of rise, but let's just use that as an example. We realize that by minute 8, the negative rate of rise has double the amount of acidity that you have if you were using the slow start. So, in short, our take-home message is that the way you roast affects the behavior of the titratable acidity duration. But comparing our 3 different origins, we saw that there were no significant differences between the 3 origins in terms of titratable acidity behavior. Now, one hypothesis that we have is that this could be because of the fact that initial titratable acidity for all 3 origins were pretty much the same. We were close. So maybe this is why we are seeing that there's no significant differences. So to validate this result or to investigate further, we can pick other origins that have differences in initial titratable acidity and necessary and see what happens during that roasting. Now, this graph shows the behavior of pH, which is basically the oxygen or the trait of titratable acidity. So while TA increased to a peak drop, a pH dropped to a minimum peak, but then increased again. So now I get to discuss color results. And then before I switch gears to the color, I'd like to mention that the next steps for the acidity is to look at how the individual acids are also behaving. Because we learned that for example, that's something the sum of all the specific acids that you have, like chlorhydric acid and the formic acid, for example. So it'd be of interest to know how these specific acids are behaving and how we can correlate it to the flavor of our coffee in a certain perspective. So that's the next step for the acidity results. Now let's look at how those things affect color. Okay, so as coffee people, we care about color a little bit. Not even let's short to buy coffee, and when you're looking at light, medium, and dark. And I make these decisions based on the color of the coffee. We also care about color because it's used as an indicator of roast degree or roast level, which I just explained. And it's also used as an indicator of quality. If you go and buy a coffee bean and it looks dull, it looks like they have different colors in there, your mind automatically tell you that we are talking about very high quality. So color matters a lot in coffee roasting. And thirdly, a lot of people use color as the end point of a roast. So instead of roasting for 60 minutes like we did, people can decide to roast up to a certain specific color. So color is an important character. Now, what at all is color? So to be able to perceive color, we need three things. First, we need a light source, or how many letters being shown onto the sample. We also need an object, which in our case is our coffee. And then you also need an observer. So all these three things must be present until we can understand color. Now, in the coffee industry, typically, color is usually used to spectral photometer. So the first one is the actual photometer, and then the second one is the phantom. Now, how these work is that you typically grind your sample, or you need a whole beans. You put it in a container, as you see it being down here, and then you put the color, this black color onto the container that you saw at the big wheel. And what happens is that the system makes a very bright light, and then the reflectance of that light which is measured to give us power coordinates. So for experiments, the power stem or the power space that we used was the CIE LED power space. And that's how it works. It has three coordinates. They have the L coordinate, the A coordinate, and the B coordinate. The L coordinate represents the lightness. So that will be this line. And it ranges from 0, which is black, to 100, which is white. So your green coffee will fall somewhere closer to white than black. So your green coffee can have an L coordinate of like 60. And then it has an A star coordinate, which goes from negative 60, which is green, all the way to 60, which is red. So again, your green coffee should have lower A coordinate values because it falls here on the here. And then one also has a B coordinate that also goes from negative 60 to 60, but this time is linked together. So let's look at how using this system, color of our coffee changed during our roast. So first, this is the same skill that we just saw, and then this is an actual picture of how the coffee colors look when we grab the samples. Now this graph is showing how the L coordinates behave during roasting. So we can see that with the red color when you have the L, it starts with an L of about almost 65, which makes sense because when you're black to white, 65 is closer to white, and your green coffee has an L coordinate that should be closer to 100 than 0. So what we are seeing here is that your L coordinate starts from around 60. It increases slightly because at the end, your coffee is yellowing. It's kind of getting a little bit lighter, and then it starts browning. So your L will start dropping as the roasting is progressing. So this is why they are seeing this curve here. Now, if you look at the A curve, you see that it starts from around 2, which means more red on the red and the green line, and then it increases. That means, say, it's not 1 out of 2. That means it's more closer to the green in the A line, and then as it browns, it gets closer to the red line. So that's why I see an increase and then a decrease in the A coordinates. Now for the B coordinates, that's the blue to yellow line. You see that it starts with around 3 to 4. So that's your coffee is closer to the yellow section, and then it increases. Your coffee gets more yellow, and then it starts browning. So it starts dropping and gets into the negative B values. So again, back to our main question: how do the different roast profiles affect the color? So these 3 graphs are showing 3 different roast profiles. We have a fast start, a slow start, and the extended Maya. So here you can see that the progression of the L is different depending on how you are roasting your coffee. So the color changes that you'll be observing as roast depends on the roast profile that you are using. Because, for example, if you look at minute states, the L value for slow start is still very high as compared to the minute state of fast starts, which have already started running. Okay. Now, a very exciting discovery here for any that we made was that when you plotted our L, A, and B coordinates on a 3D curve, we saw that regardless of the risk profile, regardless of the origin, our color value fell on the same curve. They follow the same curve. So we decided to call this a universal color curve. So this began here with the showing the universal color curve, and the circles are just showing the different faces that we have, or the different demarcations. So the first circle, the color change, then we have our color change to first part to second, and then to second. So we combine all our samples together. So these are all our 6 system samples, then all their color fell on the same curve. Now, to test if this was truly universal, we compared it to other authors or scientific papers who have also measured coffee color using whatever it was that they had. And this is what we saw. So this curve, it's showing our data is the gray ones or the very dark ones, and then the different papers that are compared, it's the different colors. So we see that by superimposing other authors, it also follows our 3D color curve. And the very fascinating thing that we saw, and we picked the paper that was on red, and we used their color values, we added it to our curve, and that's the navy blue one, I don't know if it's very clear from there, but that's the navy blue point, and you see that it falls right in our curve. So what this is telling us is that basically any maillard reaction process or food process will probably also follow a color curve. Well, when we care that our color values are showing on the curve, that's stopping people. And one thing that has been a big issue in the industry is how there's no standard to name our coffee. Say, for example, what I'm calling will be someone's legume and vice versa. So with having quantitative results like this, what we can do is we can set thresholds or limits to what someone can call nice. We are currently working with the SCA to develop a coffee color dictionary where you can define the color of coffee based on actual quantitative color measurements. So that's one way that our color curve is helpful. So this is where we are right now with this research, and hopefully next time I'll be here to give you more updates. Thank you so much, and I'll take your time.